Hello and welcome to the XP Solutions XP Live webinar. My name is Jessica Jeffries and I'm the Products Manager here at XP Solutions for the Asia Pacific region. This morning we're broadcasting from Brisbane with our guest presenter who I'll introduce shortly. We really appreciate your time joining the webinar today, in particular for those of you that it is close to the end of your day. And as you'll have already seen, today's webinar title is Modelling with Different Cell Sizes and is part of a 2D modelling series. The webinar should be useful to you whether you're new to 2D modelling or looking to get into details of the theory, setting up and running these models. We will first run through a presentation followed by a software demonstration, and you'll be able to find this webinar and other recorded webinars on our website at the address shown on your screens now. We're lucky enough today to be joined by Bill Syme as our guest presenter. Bill has 25 years of experience working on riverine, estuarine and coastal studies, of which most have been in the flood hydraulics field. He has successfully managed and led a wide range of flood studies in Australia and overseas. Bill is also the author of the XP2D engine. Bill manages software operations at BMTWBM and provides specialist flood modelling and management advice. Welcome, Bill.
Thank you, Jessica, and thank you all for tuning into this webinar. Today we're going to focus on modelling different cell sizes within your 2D model, and we're going to look at how and why we would do that. We're then going to look into the important issue of how you would review that model results. Then following that, Jessica will give a live demonstration, followed by some question and answers in the latter part. Firstly, I just wanted to give you a bit of an overview of the 2D solver that is used in XP2D. Importantly, it solves the full 2D surface water hydrodynamic equations, and it's not a simplified scheme where some schemes just take the 1D equations or diffusive or kinematic equations over a 2D mesh. This is actually solving the full 2D equations. It's a second order solution, so that's another level of accuracy that's often needed in areas of complex flows. It also solves the full equations in the sense that the inertia and eddy viscosity terms are included. The importance of that is that you'll pick up the effects of cross momentum and horizontal energy losses, such as at a river bend or something, through a structure, basically wherever the flow is very complex and changing direction rapidly. A full 2D scheme will pick up those losses very well, whereas 1D ones will not. Importantly, it can handle fluid numbers greater than 1 by automatically switching to upstream control flow regimes, and these are supercritical or weir flow, depending on the slope of the terrain. There is no artificial adjustment of Manning's ends with depth for stability reasons or other reasons, but you can vary your Manning's end with depth should you choose, such as for direct rainfall models. It's an implicit scheme, which means it's operating on a current number greater than 1, and that therefore allows large time steps and no need for adaptive time stepping, which has benefits. In the UK 2D benchmarking, which some of you would be familiar with, it is one of the top performers, and it was often faster than many of the parallelized schemes. And probably one of the biggest strengths with the 2D engine is its actual linking capabilities with 1D schemes, and I'll show a slide on that in a second. So the equations that you'll see in a second are the full 2D equations. They are solving not only how the effect of gravity and bed resistance, so they're your fundamental ones, but also includes inertia and eddy viscosity turbulence. It also includes effects such as Coriolis and atmospheric pressure and external forces, which are not so relevant for flooding. But the remainder of the terms are all important in different degrees depending on the complexity of the flow and how deep the water is. The 1D, 2D dynamic linking capabilities within the 2D engine are very, very powerful. Effectively across, you can see on this image here, there's a 1D channel going down the middle, and the overbank areas are carried out in 2D. So you can get the effects of when the flood totally dominates the channel and goes across it, you get that momentum preservation across that 1D channel through those 1D, 2D interface links. It can also handle strong parallel flow to a 1D channel. So down the bottom right, you can see the velocities down through the 2D and the velocities within the 1D effectively parallel or close to parallel, and it has no problems handling that situation either. Across the interface, the effects of upstream control flows are also included, so it will switch to that weir flow. So the 2D solver uses a fixed grid, and we'll just have a quick look at some of the pros and cons of a fixed grid. They are very quick to set up, very, very quick to set up, which is their big plus. And when you're doing your impact assessments, there's generally no need to change your mesh, so therefore your base case results don't change. Effectively, once you've got your model set up, your mesh doesn't change, and that is very useful in terms of not getting spurious effects away from your impact assessment area. It runs on a fixed time step. You do have adaptive time stepping options, but normally fixed time step is preferred because it means that every solution before and after scenario you step through at the same time. Adaptive schemes will step through at different speeds depending on changes to the topography, and that can give you some spurious impacts elsewhere. Very fast. Particularly the 2D solver that we've got here, it's very fast when you're considering the same number of elements. There are negatives though, and those are if your grid is too coarse in key areas of your model, then the hydraulics is not well resolved. So that means you may need to go finer. And of course, if your resolution is too fine, you have an excessive amount of elements, and that will lead to very long run times. So it's getting that balance can be tricky in certain situations. So why model with different cell sizes? The key is this will give you a faster running model, and it will give you the ability to put a finer grid over the area of your interest. And this can be done by either using linking 2D grids and or using 1D networks to represent your in-bank areas. The important thing here is that halving your cell size will increase the runtime by a factor of 8. So if you change your model from a 30-foot model to a 15-foot model, your runtimes will increase by 8. So if you have a 1-hour simulation, it will become 8. So we need to try and optimize models that become too long to run by using coarser grids in areas where you do not need that fine resolution. So it's all about improving your results. On the left of the screen there you can see a 20-meter resolution model in the area of interest of a breach. And as you can see, the flow patterns aren't particularly realistic. The water is going straight through these buildings in the middle there, and it looks very chunky. If you move to the middle image, you have 10-meter grids. And that's starting to give a bit better representation, but it's still not picking up all the flow paths. The far right image shows 5-meter resolution, and that's now giving you the sort of effect that you would like if you're looking at this area in the near field. And going to smaller resolutions beyond 5 probably would have little benefit. The concept that we have here is to try and optimize your mesh resolutions in different areas. So here we have a model, and our area of interest is shown by the yellow ellipse in the middle of the screen. So in this area we needed a 2-meter resolution to be able to assess the various proposed development options for this site. But if we made a 2-meter model for this whole model, it was going to take a long time to run, and we would not be able to meet our deadlines. So what was carried out was to use a 5-meter resolution in the red zone, a 5-meter resolution in the blue zone, and because the 5-meter resolution was too coarse for the in-bank channel representation, we've actually replaced the in-bank areas through those two 5-meter grids using 1D cross-sections. There are also areas inside the green zone, the 2-meter grid, where we have some structures, some 1D culverts. So we have some embedded 1D culverts in the middle of the screen. So the approach here is to put your coarse grids away from your area of interest, or for example in rural areas, and your fine grids where you want them. And if you need to, you can use 1D solution if your coarse grid gets too large to represent the in-bank areas. So suitable applications. One example would be having a river represented using a 1D network, and you had several towns along that river, where you can model each of those towns using a different 2D grid. And as you saw from the previous example, you can use linked 2D grids to transition between coarse and fine and back to coarse again if needed. And this allows you to put that fine grid over the area of interest and coarse grids elsewhere. Another common application is using a finer grid over the urban area and a coarser grid in your rural areas. And of course, you can have a combination of those options. Let's look at how the 2D interface and the 2D-2D interface and how it works. This is when we're transitioning from one grid to another. And we've designed this so that you can transition from one grid to another of any sort of resolution and any orientation. Effectively, what you do is you digitize a 2D-2D interface line. I sometimes think of it as a stitch line where you're stitching these two 2D areas together. And at each of the vertices along that 2D-2D interface line, a water level control point is inserted at the yellow squares on your screen. The 2D cells along that 2D interface line are selected and associated with these water level control points to transfer water through from one domain to the other. So as you'll see on the screen, you can see the water transitioning from the coarser grid on your bottom left through to your finer grid on the top right. One very important feature of this 2D-2D interface is the ability to preserve momentum across that line. The assumption is that the velocity does not change across that line. So it's not like a system where you pick up the water on one side and deposit it on the other, such as you would have using a Weir equation or similar. The approach here is to assume that the velocity is unchanged and therefore to apply the full 2D equations across that interface and therefore preserve momentum across that 2D-2D interface line, which is a very somewhat unique and very important feature of this capability. Now effectively what happens along this 2D-2D interface line is that each of those water level control points, the water level that is applied to the 2D cells along that interface line is interpolated between the water level control points. So for example, the top left, so between two of those yellow squares, the water level applied to those 2D cells is interpolated linearly in between those two squares. So on the left side there we have quite a good representation. But if we start to have a big distance between our water level control points, so on the bottom interface here, there's a yellow square on the left, and then there's the next yellow square is actually off the screen. And therefore the water level that's being interpolated along that bottom line is a linear interpolation over a long distance, and that may not be representative of what's actually happening in reality. So what can happen in that situation is sort of unusual flow patterns can start to develop. You can see here the water's sort of squirting in on that corner and then heading straight back out again, and the coarser grid underneath that is also sort of having a similar flow pattern. And basically what you're seeing on the screen there is not that realistic. So what can we do about that? Well, the trick here is to make sure that you've got sufficient water level control points to reproduce the water level profile that will be occurring along there. And when you have a long distance without them, you can actually automatically insert more points by using the dialog on your screen. You now see, once we've inserted those extra water level control points, the flow patterns are looking much, much more realistic. Occasionally you may not want to insert additional ones, and that would be possibly across a deep water river crossing or so forth. So we give you the option, and we'll talk about that a bit more later on. The other thing to note is that it's good not to have your water level control points too close, and you want to have them about 2 or 3 times, certainly not less than 2 or 3 times the distance of your larger 2D cell size. Let's look at an example application. On the right of your screen is an urban area nestled within a rural area. So we're going to look at modeling this area using just a simple, we'll represent the in-bank areas using 1D. Then we're going to model the overbank areas with a 10-meter grid, a 2-meter grid, a 5 and 2 meter combined model using the interfacing I've just described. And then very importantly, like with all modeling, you need to review your results and make sure that it's working as you think should be. So here's our model. Effectively, the blue hatched areas are inactive areas, so where the 1D model is coming through on the bottom left and through the top right, that's open channel, so we need to deactivate those cells. We've also decided to deactivate the buildings in this model as opposed to using a higher Manning-Zen or other methods. There's a pipe network system underneath the urban areas. In fact, there's a major trunk line that replaces the creek sections. So when we use a 10-meter grid, which you can see as the grey background there, these are the results that you get. And they look reasonably sort of representative, but they are fairly coarse. When we move to a 2-meter grid, you get a much finer representation and detail of the flow patterns, to the point where the velocities are so dense that it's very difficult to see on the screen. So let's just zoom in and have a closer look. So now that we've zoomed into the bottom right of the model, you can see here the flow patterns that are developing in that 2-meter resolution, much more detailed than what you would have with a 10-meter resolution. So if you like, this 2-meter grid model could be our benchmark situation. Let's now look at how we would set this up using a 1D, 2D, 2D modeling approach. So what we've done on the screen here, we've changed the 10-meter grid to a 5-meter grid. We still have the in-bank open channel areas modeled in 1D, and the area shown there in green is actually a 2-meter mesh. We've decided that this is our focus area, and we want to model that using a 2-meter grid. And this is effectively the flow patterns that you'll see develop near the peak of the flood. So you can see where the very dense black is, that is where the 2-meter grid is in action. And where the 5-meter is in action is where the velocity arrows are at a bigger spacing. So we've developed our 3 models, and what does that mean in terms of runtime? For this little model, which is a very quick running model, the 10-meter grid takes 0.01 of an hour. The fully 2-meter one, single grid 2-meter model takes 0.38 hours. And then the 5 and 2-meter ones take 0.07 hours. So if the 0.38 was too long, although that's very quick, but if that was a larger model, then you need to move to embedding your 2-meter resolution into where you want it for your area of interest. And that will reduce your runtime significantly in a model of this nature. So we now have our 1D, 2D, 2D model. We now need to review it. The main way that we review the 2D, 2D interface is to check the flow patterns. And just make sure that the logic of using those water level control points to represent the water level profile between the two 2D domains is appropriate. And there's some fundamental checks too, such as making sure that the flow is occurring between your 2D grids. Another useful thing to do, if possible, is to actually review your linked model, your 2D combined model, with a fine grid model over the whole area, which of course would take longer to run, but you would only just do the one simulation of that to compare and see whether you're getting similar water levels and flow patterns. So here's our 10-meter results zoomed in, and as you can see, the flow patterns are fairly, represented very coarsely, and but it gives some sort of representation. If you now look at the 2-meter grid results in the same area, you see that you get a very fine resolution, as we showed earlier, and it looks much more representative of what you would expect. We're now going to review our 1D, 2D, 2D model results and compare them with those 2-meter grid results. The first thing you may notice in the top right is that the water is doing some strange things. We have the 2-meter grid flowing down the road and then squirting around an obstruction in the top left there inside that ellipse. And on the right-hand side inside the ellipse, the same effect is happening. The water is squirting around and back onto the road. And closer inspection, we notice that the 2D link line has not been digitized along that top section. So there's actually no water flowing between those two 2D grids. So that's a fairly fundamental check to just make sure that wherever you're wanting the 2D grids to flow between each other, just make sure that 2D interface line is there. The other area that may be fairly obvious is this problem of strange flow patterns developing, and we've got that as an example in the bottom left of your screen inside that light green ellipse. As you can see, there's very strong sort of weird flow patterns developing around the corner there, and as I explained earlier, that is due to not having enough water level control points along that long line at the bottom of the screen there. So along that long line, the water level is being interpolated between the two control points inside the yellow circles. And that will give a very poor reproduction of the water surface profile through that area. So let's see what we can do about that. The next slide shows results after we've replaced the 2D, or inserted the 2D interface in the top right of the screen. So we're now seeing the water transfer from 2D grid to 5-meter grid very nicely down the road on both sides of that ellipse. Down the bottom corner, what we've done for this simulation is to insert an extra vertex inside that yellow circle. And you can see now that the flow patterns are much more realistic and we're not getting those strange and weird effects. The next stage is that because we've got this 2-meter grid model over the whole area, we can compare the flow patterns in that with what we're getting in our 2D model. Now you may need a keen eye, but inside the blue circle, this is the results of the 2D model. You can see here that the flow patterns are not particularly good as it's going around that bend. It seems to be pushing right up into it. And I guess it does take many years of 2D modeling to appreciate that that's not quite right. If I now show what the 2D grid-only model results looks like, you can see there that the flow is, you're not getting those high velocities pushing right up against those houses. And once again, the reason for this happening in the 2D model is because the water level line control points are very, very sparsely spaced. On the next slide, we've rerun our 2D model with automatic water level control points every 20 meters. So that's roughly every 4 cells of the coarse grid. And if you go and have a closer look inside that blue corner now, we are getting flow patterns which are much more realistic compared to the 2D grid-only model. The The slide doesn't show the inserted automatic ones on the screen, but they are there every 20 meters. I'll just have a closer inspection of those flow patterns. So on the first zoom is the original 2D model results. The next one is the new 2D model results with your water level line points inserted every 20 meters. And that's giving a much better representation of the flow patterns around that corner. And the final one is the original 2D grid only. You may also notice that this 2D grid only model doesn't have any flow coming through from the bottom left of the corner, bottom side of the screen there. And that is because this has a different orientation and is a consequence of using building outlines to block your buildings. So you do have to be very careful about blocking out your buildings, that you may be constricting flow in certain areas. So just to wrap up, we'll just have a look at some general rules in setting up these 2D models. Effectively, grids can have different orientations and extents. There's no constraint on the number of grids, there's no constraint on the orientations, and there's no constraint on the extents. However, it is important with regard to the cell sizes of those grids that you avoid having a transition ratio greater than 10. So for example, it's not good practice and you'll have problems if you try to go from a 100-meter grid to a 5-meter grid. In the example on the right, this model has a 10-meter grid through the town. There's a 2D interface line along the levee, which is about 3 or 4 meter drop into the town, transitioning to a 30-meter grid in the river. And then that 10 and 30-meter grids are actually nestled inside a much larger 60-meter grid model of the river system. So if you do need to go from a large to small grid size, have several domains. Some tips for where you locate your 2D interfaces. Generally, what you do want to avoid is areas of rapidly changing flow direction. The one exception to that would be potentially flow across a levee bank, such as shown in the image on the right. But avoid putting your 2D interface hard up against a building where the flow patterns are rapidly changing around that building. Rapidly changing terrain also can cause problems, such as across a riverbank, because the different cell sizes and different elevations along the interface can cause some issues. Generally speaking, though, it's not too much of a problem, but you may get issues in those areas. And importantly, place your 2D interfaces around your area of interest and not through. The purpose here is to allow you to transition to a finer grid so that you can reduce your run times and end up with high quality results in your study area. Some general rules for time steps. As the 2D solver can handle current numbers greater than 1, the time steps can be fixed and can run along quite happily. Each 2D grid can have a different time step. In fact, you should have a different time step for each grid. The only constraint is that the time steps must be a multiple of each other. If they aren't a multiple, the time steps are automatically adjusted by the software. Just as a quick example, if you had a 20-meter grid and a 10-meter grid, 10-second and 5-second time steps, there would be no automatic adjustment. If you had a 20-meter grid at 10 seconds, but your 10-meter grid was at 4 seconds, the time step for the 10-meter grid would be adjusted down to 3.333 seconds. And as a general tip with this 2D engine is don't try to solve instabilities by simply reducing your time step. Instabilities are nearly always as a consequence of poor data or model setup, and indicator of whether your model is well made or not. So effectively your 2D time step should be somewhere between 1/5 and half of your cell size measured in meters. And if it isn't, then there's normally 99% of the time something else that is wrong, which we'd be more than happy to help you out with. Well, thank you for listening into that. Jessica's now going to give a live demonstration of the software, and so I'll hand it over to her.
Thanks very much for that, Bill. And just while I get that demonstration up on your screen and ready to go. I'd just like to thank Bill for sharing his expertise there on setting up these models and the things we need to look out for, obviously from his experience with working with the engines and from building many models. So the first thing I wanted to do was, before we actually look at the details of setting up these 2D interfaces and multiple domains, was to actually show you how you can pull out some of the information about the 2D models, such as how long they've taken to run. And what we have under the Analyze menu is a 2D simulation summary. That 2D simulation summary is really useful as a way of having a quick look at our model settings, doing a health check on the model essentially. So the top section of this interface is a table, and it shows us all the input data and also shows us the build of the engine that's been used. And there's codes for the engine build, so this engine has the AC code in it. And this version of the engine has some improvements specifically for instabilities occurring at 2D interface lines. It'll be available in the next service pack, but if you want to get access to that sooner, please do get in touch. The ability to model multiple domains, multiple grids, is available in the software now, and if you've got the multiple domain module already, you might have used that. If not, then if you're interested, get in touch again with our team. At the bottom of the screen we have some graphs, and these graphs are really useful for having a quick look and seeing what's going on in the model. The things we're looking out for are things like a spike here. Now, it's not so unusual to see a small spike at the start of a model, and the math error isn't getting too large a number, but certainly on the flow in and flow out graphs we should also have a look and see if we've got any spikes or if those flows are changing smoothly throughout the model. So just wanted to show that and make sure that you were aware that was there, so that you can have a look at the runtimes of your models and so on. So moving on to our first attempt here that Bill's discussed for the example model, we have already loaded in here 2 different grids, and it's very easy to set up multiple grid layers when you have the multiple domain module. Simply a case of right-clicking on that grid extents and adding a new layer. And what that does is it gives us multiple layers underneath that first layer. Then when we have added a grid, we can right-click again and we can open up the Properties dialog box. And this Properties dialog box is where we need to make sure we set to override the global time step. And what that allows us to do is to have different time steps for each of the grids, and that's a really important part of making our model faster. As you can see, we also have the ability to change the orientation and so on. So putting in those grids can be done by importing from GIS or by using the tool on the right hand side in the toolbox to just digitize the grid. And that tool is the polygon tool, and we can, as I said, just draw that in if we don't have the grid layout in GIS form. Once we've added the grids, we have to add the connection. So we have a 2D interface layer, and if we right-click on the 2D model, if that layer doesn't already appear, we can add in the 2D interface layer. Once we've got that layer added in, we just make sure we select the layer, and again we're going to use a tool from the toolbox, or alternatively we could import from GIS. And this polyline tool, if we use it in conjunction with the snap functionality, allows us to snap to the edges of the grid that we've added. So when I hover over a corner, I can actually click and select one of those grids, And there's keyboard shortcuts here that allow me to automatically select the outline of the grid, which hopefully you can see showing up in red there. I'm holding down Shift, which goes in one direction, Control goes in another direction. So we can click on that point, and then very importantly, if we are doing a nested grid like this, we can close the grid to make sure the 2D interface appears across around the whole of the grid there. So once the 2D interface has been drawn, there's another step which we have to make sure we complete, and that's to make sure that we connect the two grids together. And we do that by right-clicking on the 2D interface and selecting the Edit Data option. Once we're in this dialog, we can then choose the grids that we want to connect between. And if you only have two grids, it doesn't matter which order you connect those grids in. If you have more than two grids, obviously the order still doesn't matter, but we should make sure that we get the right grid. So that's how we actually set up our multiple grids and our interfaces. But as we saw, this first attempt at our model produced some slightly unusual patterns within the flow and the velocities that we saw occurring. So our second option was to add in an additional vertex to the 2D interface. Even that wasn't enough to solve all of the issues that we noticed. So it would be very simple to then edit that 2D connection and put in a minimum distance between those water level control points. So that's just shown on your screen now. Again, access through the right click and edit data on the interface line, and that helps us to avoid instabilities, avoid unusual flow patterns as well. Once we'd done that, we had an improvement in the model results, but I've got a final version of the model here where we've actually also moved that interface line very slightly. So the location of this interface line away from areas of unusual flow patterns can also help to avoid anything like that occurring. So you can see if we just flick between those two models, we've moved the interface line from its location sort of just next to one of those roads but not quite on the road, a little further out, so that the location where we had some unusual flow patterns is now included well within the finer 2D grid and not actually right along that interface line. And what we can now do is we can actually look at these results, and I know there'll be a slight delay just getting those to them, but once the animation starts, you'll be able to see the flow first coming down the river, and then if I zoom in a little bit, moving across that 2D interface and flowing across the location of the road and flowing around the houses. These sort of animations are obviously really important when we're communicating results, and very useful for presentation purposes. And just to remind you that you can use the animation tool, which I'm just pointing out at the bottom of the screen there, to actually record that animation and include that in a presentation. So I've just paused the animation, which should appear on your screen shortly. And you can see that those flow patterns are not occurring in quite the same way. We've got some water going over the interface line and just sort of flowing over that grassed area towards the road. And as we step through this now a little more slowly, we can see those velocity arrows advancing in a slightly straighter direction. So it's very useful to be able to spend a bit of time actually really identifying what's going on in the model in a lot of detail. Showing those velocity arrows is really important when we're analyzing the flow, and actually showing them in a way that you can see the results easily is not always the default setup. So I'll just spend a moment, right click on the properties here and just show you the interface for changing those arrows. And having scaled size for the arrow head, for the length and width of the arrow, just means that we can display them in a way that's most useful. Also, if we wanted to show less arrows, we can use the option at the top to skip some of the results. And if I just click OK, it just skips every other result. And we can see there that the screen updates and it's just a little less compact with those arrows on there. So just thought it's worth mentioning that, because obviously looking at these, exactly what's happening with the flow is much easier with the arrows than with the depths occurring there. So that shows the example model and how we've actually quite quickly built up multiple grids. Setting up those grids, as you can see, is going to take much less time than waiting for a longer model to run, especially when you're talking about factors of 8. So we'll say thank you to you for listening and joining us today, and thank you to Bill for his time on the presentation, both in preparation and actually presenting it. Thanks again.